What's up, everybody? Just doing some impromptu online office hours. We'll see if anyone appears in the chat. But got sidetracked today. I had to make some calls and then went on a beautiful walk around campus. Probably got a little bit sunburnt, but got the chat going now. So if you're here, feel free to say hi. And I have a message on my door knocking. Brian will answer. So hopefully, okay, we'll go over here. If anyone appears, I might have to go, but I was like, since no one's here right now, we're going to try streaming. It's the week before spring break, which can be kind of slow. So I was like, let's hop online, let's stream, and if someone appears, we will answer. Is Mubot? Mubot needs to be rewoken up right here. We'll try to do a problem or two. We'll see how many we can get done. We'll see just what happens today with office hours. We're going to go over the quiz right now. So let's pull up the quiz questions, and let's maybe do a few of the regression solver ones. So going over here. Okay, look at this manager at a bookstore problem. So this is a really great one for the regression solver. So let's put in the notes, bring up the notes, office hours, notes, manager at a bookstore problem. Okay, so this is chapter 7 quiz, manager at a bookstore. So stat 201, chapter 7 quiz, the manager of a bookstore. So this problem right here is a regression problem, as we're doing chapter 7, and to solve it, we are going to use the Regression Solver Pro, something I created a little while ago. And to find it, you go over here to the Modules section on Canvas, scroll down to chapter 7, and under chapter 7, you will see Regression Solver Pro. So go ahead and download the Regression Solver Pro. We're going to download it here in the background and just open up the Excel file. So that's all you're doing right now is you're downloading the Regression Solver Pro found under the modules. I'm enabling editing, and we have it open. I think we're good to go now. Let's take a look here at the screen. Got so many things open. Okay, Regression Solver Pro is open. In the Regression Solver Pro, you see two areas. One area is down here where you put in the data. Don't put in numbers like I'm doing. I'm just showing you how it works, that it'll solve these values. It'll solve the intercept, the slope, the correlation, the standard deviation of x, standard deviation of y. The things we really care about are the B0 and B1. That's the intercept and slope coefficient. You could also have where you have the correlation and you put in the correlation value, the standard deviation of x, standard deviation of y, the mean of x, the mean of y, and then it gives you the equation, the intercept and the slope. So we're going to rewind time here, and now we're going to use it as is for this problem. So let's go to the problem. Well, there we go. So now we're over here at the problem. With us being at the problem, we're going to go and take the data. Now, there's two ways to solve it. We could enter in the summary statistics down here on the bottom into the top portion, or the data. I like doing the data way of doing it. Click right here to copy to clipboard. Hit Control-C or Command-C to copy the data. Now, go over to the regression solver and usually paste it over here on the far side. Now, with the data pasted, you want to know what is the x and what is the y. The y variable is the thing we want to predict. We want to predict the sales in thousands of dollars. That would be right there, $10,000, $25,000. Hold Shift and click the last number, then hit Control or Command-C, and since we want to predict it, it goes in the y. Do not paste over the y right there. Don't do that. That'll break it. Now click the x variable, the first number, hold Shift, click the bottom, and then hit Control-C or Command-C, and then paste the data here. You've done it. Now you have the answers. These are now the intercept, the slope. It's solving out the equation for you. We will not ask you to solve like mathematically the equations. Some of them are in the slides. We don't solve the equations for intercept and slope. We don't, it's just more math than we like to do. So all we have to do now is take these numbers. Let's put it in a dual screen side by side so you can see it. So we get nice and zoomed out right here, and you can see the screen. Let me remove where I am at. The intercept is going to be this first value, but it doesn't ask the intercept first. It asks the slope. So we can take the slope. It says to 3 digits. So we're just going to round this down to 3 digits. Good to see you, Para. Well, that's awesome. Well, thank you for swinging by. We like helping out with all the math and statistics here, and that's what we do here at Stat 201. We'll throw you some points. What does B1 mean? The slope is for each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. So we are predicting the sales at a bookstore. So for each additional worker, we expect sales to increase by this amount times 1,000 on average. So on average, this means that for each additional worker, it means that on average, an additional increase is associated with each additional person working. That should be right. Let me look at the other one in sales. There we go. It should be on average that an additional increase of this times 1,000 in sales is associated with each additional worker. Now we have the intercept. The intercept is the value of B0, which is when X is equal to 0, we expect Y to equal B0. I just want you to think over that interpretation. When X is equal to 0, we expect Y to equal B0 on average. Notice how I say 0 twice. And even with the slope, I say for each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. It kind of helps with remembering B0 is the intercept, the value of X, or the value of Y when X is equal to 0. And B1, for each 1 unit increase in X, we expect Y to increase or decrease by B1 on average. So this being the intercept would be when no one is working. When 0 people are working at the store, we expect the sales to be 7,860. So yeah, it'd mean on average, the expected sales with 0 people working. That sounds about right, which is illogical because we wouldn't make money. It does not make sense because it's unlikely we would sell anything with no one working. Now that we have the equation, we can take these numbers and we can just plug them in. B0 is going to go right here for the intercept. This is B0. We'll just write it in. This is B0 and this is B1. So you just plug in the value of B0 here, and then you plug in the value of B1 here, which is the slope coefficient. Now we're going to predict the value with 19 people working. So not that hard to do. All we do is take this value, and it's important to know your notation. Got to know your notation, brother. So all we're doing is taking 19 people working, which is X, the amount of people working, and plugging this in just there. So we're just going to plug 19 in and solve the equation for predicted sales. Predicted sales. So we're predicting the sales with 19 people working times 0.863. And then we add to this 7.860. And that is the predicted sales in thousands of dollars. Just plug in, and this is not the actual sales, it's the predicted sales. Now it does say round to the nearest $10, which means we need to times this by 1,000. Luckily for us, we can just kind of move the decimals because this is going to be right here, 24,257. Rounding to the nearest $10 is going to do this. Remember, the number we got when we did this is in thousands of dollars. Like if you had $24,000, move the decimals is 24,260. Now we see that the actual sales is 2,400. So when you think about this visually, you got to think about the model. Remember that we make predictions with the line. So the line is the y hat. The green dot is going to be the actual. So what it's saying here is we predicted that right here was 24,560 or something? 24,260. That is where this would have been predicted to be. And it's actually 2,400, which means it's below. And so Y, which is where it's at, is 2,400. And so that's where it's at. The model predicts much higher. So what we want to find is this residual value. And we can find it really easily because the amount of the residual is just how much it is below. It's going to be E is equal to negative 260. And this can be found that negative 260 is equal to the actual, which the actual is 2,400 or 24,000 minus, and then the 24,260. So residual equals actual minus predicted. So if we rewrite it out down here in its actual notation, actual minus predicted. There it is. Residual equals actual minus predicted is the equation. So it's negative 260 because a negative residual means the predicted is higher. And you can see that right here. Knock and Brian will answer because the predicted was higher, negative 260. And the model, be careful, a lot of people get this wrong. The model has overestimated it because here's the point, and the model is over it. So the model is overestimating. Your answer might be different. Let's check. Got 100. That's a tricky problem. It's a good tricky one, and we use the Regression Solver Pro. We love it. So it's found under the modules. Let's see what the next one is. Easy R squared. So this is Regression Solver problem. Okay. Let's do this one. Well, we'll see. I'm going to go look and see if anyone's here in a moment. And then I'll be like, okay. So this is 10, 4 to 3. And this one's going to be the R squared one. R squared is the percent of variation Y explained by the variation X. This problem really doesn't do it justice. When you think about R squared, it's how tight the points are around the model. So this model right here, the tightness of the points leads to R. So I could literally look at the correlation of this. We're doing height and weight. So I could get the correlation of this very easily by doing associate. Well, I can get it. I can just write it. Height tilde weight, comma data equals survey 10. And we can see the correlation value of this. The correlation value is equal to 0.6013. That means a positive, moderate positive correlation. The Pearson's R. Remember we talked about R. Mubot in the chat. So what is R squared? You take R and you square it. So that is R squared. And you can see R squared when we make the model. Remember, this is R squared right here. 6 times 6 is 36. And there it is right there. There is the R squared. And we use the multiple R squared. You'll just hear it called R squared in this class. Now, it is no longer a correlation. Because when you square R, if you had a negative correlation, like if this was negative 0.6, it would still be the same value, because when you square something, it's always positive. So we call it what it's called is the coefficient of determination. I guess it determines how much we understand in Y based on X, or X is in a multiple regression. So when we talk about this R squared, we say it's the amount of variation in Y that we understand from the variation in X. So let's look to see which of these makes sense right here. Remember, it is the correlation squared, and there's correlation. So all we do is we take the value of correlation down there at the bottom, and we square it. And that should do it. That is R squared, but now you square it to turn, or you times it by 100 to turn it into a percentage. So it's the amount of variation, the percent of variation. So 87.80, 87.80. So it's the amount of variation in sales that can be accounted for by a model of sales on number of salespeople working. So this is the amount of variation in Y that can be explained by the variation of a regression model of Y on X. I don't love that they phrase it that way. That's not the answer. But I really, okay, can't copy it. 87.80. Yes, that should do it. The percent of variation in Y explained by the variation in X. That is what R squared is. The percent of variation in Y explained by the variation in X. Okay, let's do another one. Another one. Where's my another one? I don't even know what's that anymore. Another one. Okay. Maybe, wait. I should take a quick look. We'll do this one. I'll look outside, see if anyone's here. 1343. This is the terabyte one. We did this one on the homework, but if we do, I'll try to do them all. We'll see how many we can do. Disk drives are getting larger. So this one deals with R squared first. Ooh, we love R squared. So it's correlation squared. Unfortunately, it does not give us the value of correlation, so we are going to go find it ourselves. Make sure to download the Regression Solver Pro. The Regression Solver Pro can be found over on the page, our class page. Go over here to the modules. Under the modules, you will see Chapter 7. Under Chapter 7, you will see Regression Solver Pro. We are going to enter the data into the Regression Solver Pro. So I'm going to unwind time. There we go. And we are going to enter the data here under the X and the Y. Do not put the data in on the X or the Y. So now that you have the Regression Solver Pro, go to the data, and now click Copy to Clipboard. Click Control-C or Command-C to copy the data. Go over here to the Regression Solver and paste the data. Now, the reason I do this is we have to understand what we want to predict. We want to predict price because price is the variable of interest. We call it the Y variable of interest. And we're going to click the top number, hold Shift. JC, good to see you. Oh, wait, did I... Oh, millions watching. That's so nice of them. JC, are you here? Or because I know I think JC sometimes swings by. I put the sign on. I'll go outside if I was like, I'll stream. What's up, JC? Oh, people are so nice. People are so nice. I appreciate kind people swinging by YouTube, and everyone is always welcome to swing by. We welcome people from all around the world here, and we also will help them learn stats if they got stats questions. Look at that. We got the correlation. And then how do we get r squared? Equals this times this. R squared. So literally just take that value and square it. And that's r squared. So we now have the value of correlate r squared, but also make sure to move the decimals. So it wants to 2 decimals. And there we go. 98.3% of the variation in price can be explained by the capacity of a hard drive. Well, then they asked what it means. So 98.3% of the variability in price of these disk drives can be explained, can be accounted for by a linear model on the capacity of the drives. That should do it. Woohoo! I'll be right back. Take a look at here. I'm back. Let's try to do 2 more tough ones here. That's easy. We can do easy ones. Those are so easy. A lot of people get stuck on this one, so let's do this one. So, and JC, how you doing? I guess we're gonna do like 30 minutes of videos. What's No, you're Brian, not back? Oh, I'm not. I'm back. I get it, Dee Dee. I get it. And good to see you here, Dee Dee. We'll throw some points. We're gonna do like 2 more questions. I'm gonna hop out and do some in-person office hours. Brian took a walk around campus and maybe caught some Pokemon today. So researchers collected. It's just such a beautiful day, and there's this group thing on campus, and I just got talking to like a bunch of group people after I made my call, and I was like, dang it, it's just nice. It's nice talking to students. Like, it's nice just like asking them how their day's going and stuff and all that good stuff. So here we are on mortality rate and calcium. Now, this question requires you to have a little bit interesting of knowledge of how water physics works. My day's going good. It's a beautiful day here in Tennessee. It's beautiful. I mean, like literally one of the guys I talked to was like, it's beautiful. I was like, it is. It's very beautiful here. Is this a positive or negative correlation? It goes like that. That's a negative correlation. So negative correlation is as one variable goes up, the other variable goes down, or vice versa. As one goes up, the other goes down. They go in inverse direction. That's what negative correlation is. 10 out of 10 day in Tennessee. We say it's only 10 I see around here. So there's I got dad jokes. There's a fairly strong negative linear relationship. Now this is where water knowledge comes into play. My New York accent. Towns with harder water, which means more calcium deposits in the water, have a higher mortality rate, or lower. So higher calcium, lower mortality. Why it is?
It doesn't matter.
Who knows? So there's a very strong negative. Towns with harder water tend to have lower mortality. Now this is where we get into the output. And this is where it's important to know when you look at the output where the slope and the intercept are. We pointed this out in class that there are 4 things to know in this output. You should know the coefficient of the intercept, the coefficient of the slope, the statistical significance of the model, and the r squared, which they've already times by 100. So these quantities are the intercept, b sub 0. B sub 0. When x is equal to 0, expect y to equal b0. So this would be when a town's calcium is equal to 0, we expect the mortality to be equal to 1,711. B1 is, for each 1 unit increase in X, we expect Y to increase by B1 on average. So for each 1 unit increase in calcium, we expect there to be 3.048 less deaths per 1,000. I think it's deaths per 10,000 or something. And over here, the statistical significance of the model, yes, the model is statistically significant because the p-value of the slope is less than 0.05. 90.1 means 90.1% of the variation in mortality can be explained by the variation in calcium in water. So that's got the interpretations. So now all we do is take the values and put them right here. We put B0 and B1. So let's just place those values in. Remember, we just marked them a second ago. B0 is this, and B1 is this. Make sure to put the negative. It is wrong if you don't put the negative. So now what is the slope for each 1 unit increase in calcium, because that's the X? We expect the model to predict the mortality to decrease by this right there. What does the intercept mean? The intercept would be a town with no calcium would be predicted to have a mortality rate of 17.884. Just think, if you put 0 in for X, well then 0 times this is 0, and then predicted mortality rate. So that should do it right there. The largest residual is 72.6. That residual is probably, if you take a look at this model, it's a positive 72.6. So if we had to guesstimate where that is at, probably something like this. So that means it has a positive residual, and its residual is 72.6. That means its actual value is 72.6 higher. Its residual is how much we miss by. So the town's mortality rate is 72.6 higher than what we would have predicted. So it has 72.6 more deaths per 100,000 than predicted. There's a certain town with 34 parts per million calcium. Well, that means we need to use the parts per million calcium to make a prediction. So it says predict the mortality rate of that town. So all you do here is you go in and just plug in 34. That's all you do. And so we just plug 34 times 3.048. And then we take 1711.884 and subtract from it. That we subtract the same numbers, what we do. 1711.844 minus, well, we didn't copy the numbers, what we didn't do. Let's go and do 34 times 3.048. Now copy. 1711.884. There we go. So now it would be predicted to have 1608. Is that about right? I'm going to look at the graphic. Yeah, that's right. That's about right. There, look at that. It goes in, there we go. I think the residual estimation is a little bit confusing. Oh, I'll go over that again real quick here. So this would be the predicted deaths per 100,000, round to 3 decimals as needed. And then the R squared is the percent of variation in Y explained by the variation in X. So 90.1% of the variation in mortality can be accounted for by a linear model on calcium. So the variability, that should be 100%. We did it. Let's show the residual again, because residuals are very important. So when you do a residual, like, you know how we just made a prediction here? If I had to guesstimate only the... well, whenever you do a residual, residuals are how off the linear model is. So when you look at a residual, the notation for a residual is E. And there we go. We're trying to put the line through the data. And so this has a very large negative residual. Might not have done perfect. We did close enough. This has a negative residual, negative residual, negative residual, negative. So maybe we didn't do perfect because there's not that many negative residuals. Maybe the model should have been a little bit different. And the biggest residuals are going to be ones like, this has a pretty large residual. That's not the right color. And you can kind of guesstimate these residuals, because if you guesstimate the residual, you'd look at this distance right here and you'd be like, okay, that's like, I don't know, that's 600 units on the axis. So that means it would be negative 600. No, you don't have to guesstimate. Like, here, I'll show you a model right here. You ready? To find a residual, we can do it this way. So you see, here is the intercept. So predicted height is equal to the intercept plus the slope times weight. So what does it mean? Brian weighs 190 pounds. So what is that? So do you see, we just used the linear model, and you can, if we go and look at the linear model visually, it means I am over here at 190, you trace up and you trace over, and it's about 70 right there. So Brian is predicted to be 70 inches tall. But if we do actual height, Brian is actually equal to 75 inches tall. That means, if you look at where I'm at on this model, you would use the model to make a prediction. At 190, you trace up and you hit at about 70. So the predicted is about 70. And then Brian is actually 75 inches tall, which means I'm like this, right somewhere in there. And so you're actually 75. So what is the residual? Residual equals actual minus predicted. So what is my residual? What is the residual is going to be this quantity right here. That's what the residual is. Exactly. So I'm 5. Now, if someone had a -5 residual, like let's say my friend is a -5 residual, well, where would they be at? So there's another person now, if they had a -5 residual. So if they had a -5 residual. So there could be a second person here, person 2, and they have a -5 residual. That's actually too far, but they should be there-ish. So -5. So if you're -5 as your E value, because we're going to say E equals to, which is residual equals to actual minus predicted. So you take whatever the actual is and you subtract the predicted from the model. And it gives you this distance. So they would be 5, they'd be 60, exactly. So the residual tells you how far away the prediction is. When a residual is positive, the person is above the model. When a residual is negative, the person is below the model. And if a residual is 0, the person is where? If a residual is 0, then a person is where? Think if I was like, oh, you predicted me to be 7 inches tall, and well, my residual is 0. So it's how much you miss by. That's what a residual is conceptually. It's how much you miss by. And then you can use the math to get it, like actual minus predicted. So, well, right now we should do positive. It's positive. We'll remove the negative stuff. There we go. Residual is +5. So if your residual is 0, then your actual and predicted would have to be equal. Like everybody within, I think the guesstimation trip student, I think so too. I like it because it's a very applied, like it's oftentimes how I look at residuals. And then maybe you have to learn the math first. You have to like see the math to be like, oh, it's actual minus predicted, which we do that in class too. And then you start to realize like, oh, you can just kind of look at this and be like, it's a residual about 13. Does that make sense, DD? Like when I look at this and I look at this point right here, I say, oh, that, maybe I should do the same color. I look at this and I say, this residual is about 13, because I can just look at, or 12 or 13, because they are 75 inches tall and they're predicted to be like 62.5. So they'd have a residual of 12.5. They're 12.5 taller than predicted to be. So they're way above the model. They have a very big positive residual. So, but that's how I look at residuals really quickly. I just oh, how far are you away from the model? No, I like it. It helps me understand how people learn. We're going to do one more. Then we go help students. Oof. Let's do it. We're doing some of the hardest questions right here. So people will be like, oh, this question's super hard. Let's do it. We're going to do this last one. Then I'm going to hop over and do some in-person office hours. Chapter 7, quiz. The table shows. So this one right here is the population and birth rates. And you can actually figure out the graphic without putting it into programs. Because as year goes up, rate of birth is going what? See how it's like 1965, years going up. Rate of birth is going where? As year goes up, rate of birth goes what? It starts at 19.37, and then it goes what? And continues to go what? Down. So that means the only one is this. It doesn't go random. That's random. It doesn't go up then down. It doesn't go up. So it has to be graphic 1. It has to be that just when you look. Like as year goes up, birth rate goes down. And so now, here's the problem for this one. This is where it gets a little tricky. Hey, what's up? Yep, we did homework yesterday. I'll put that in the video, JC. Thank you, JC, for asking. Let me go drop that link. We did every single homework question. Full video yesterday. Full walkthrough of all homework questions right here. Chapter 7, homework. So check this out right there. All chapters, homework 7 questions done. Completely done. So this problem is a little tricky because now we have to remove 1900 from the data. We're going to copy to clipboard, hit Control-C or Command-C, and then we are going to go into the regression solver. You're welcome, JC. To find the Regression Solver Pro, the awesome version, go to the Modules section on Canvas under Modules, and under Modules, you will scroll down to Chapter 7, and you will see Regression Solver Pro. So download the Regression Solver Pro and paste the data. So you're just going to paste data, and you're going to hope it remain pasted. Go back to your data, click the little drop-down, copy to clipboard, Control-C, click Done, go back to the data and paste the data. Now that you have the data pasted, we do have to remove the 1900 before it. It's just the way they're doing the computations for this, because it's years since 1900. I think that's... no, something went wrong here. It's incorrect. Okay, let's try one more time. So because I had that selected, it messed up. So third time's the charm. Go here and copy to clipboard. Copy. And now go back to the datasheet and paste. That looks better. Sometimes you got to do things multiple times. So now what you're going to do is you're going to take and remove the 1900. Here's how to do it. Equals, and then select the cell, and I'll zoom in here so you can see it, and minus 1900. I'll zoom in. But go to the cell. Just go to any cell, and then do equals. I'll write it again from scratch. Equals, click the cell, minus 1900. Now, just click and double click this little box. Or drag and drop. It would have had been connected. What I was trying to do, multiple times such a weird phase because, yeah, exactly. Equals, what I was trying to do right here is this. If it's connected, it would have done it. Since it's connected, it knows where I want it to go now. There we go. But you can drag and drop. So now we've got the 1900 removed, and I'm going to copy this. You can write these numbers in, but you want to copy and paste as values. So watch out right here because this is going to be the X variable explaining what the birth rate is. When you paste, it's going to mess up the reference, but go to the drop down. Under the drop down, paste values. So we've now pasted the values. You could type them in. If you can't get it to work, if you're like, it just won't work, you just go here and type 65, 70. So once again, if it won't paste for you, just start typing the values. Just start typing out the values and you'll get them in. Now we're just going to take the rate of birth, hold Shift and click the bottom one, Control-C, and now click over here, Control-V, and now take a look. Intercept, slope, R, square it to get R squared, and then we can even make predictions. You could type in 2015, because that's going to be 2050 right there, I think, right? Yeah, in years since 1950. That is the predicted birth rate, which will help us for later in the question because we can make predictions with the model. So let's go ahead and solve the question. We're going to get it side-by-side screen right here. Okay. Okay. The screen, well, was ready a moment ago. Good. So here we are with the question on the screen. The trend is generally decreasing over time because it's going down. Oh, now we need the equation. So remember, this is B0 plus B1x. Hopefully you've memorized that by now. B0 is the intercept, and this is the estimate of the intercept. 25.5, does it say 2 decimals? 5.9, that rounds to 5.9. And then B1 is going to be negative. Do not forget the negative. You do get it wrong if you don't type that. There's the negative slope. Check to see if it's appropriate. I think it's appropriate, right? It shows mostly is reasonably straight and has no outliers. There's not extreme outliers. I know these are a little weird, but nothing's perfect. So it meets the QQ straight enough. No outliers, plot doesn't thicken. Interpret the slope for each additional year. So for each additional, the number of births per 1,000 has been changing by this amount equal to the slope per year. I hate the way they say that, but that's the only one that's accurate. And I already read that. The table gives the birth rate in intervals. Estimate what it would be in 1978. Well, check this out. Just go here and type 78. There you go. And you can literally just drag, drop, and do to 1 decimal. That's got it. Now, I do suggest knowing how to do this by hand because remember, it's 1978. So you're literally just taking and plugging in 78 right here into the X variable. I'm showing it's over the X. And so you would go and type 78 times 0.11. And now you're going to take 2559 and subtract this. Yes, exactly. Going between, interpolating between the data. And notice how, oh, is it doing? Oh, because this carries more decimals. Ooh. We'll try it. We'll see both ways if it's right. It should accept both answers. It should accept both answers. I think ours is just more accurate over here. So next, it's actually 15. So how close was the model? So remember, it's actually 15. That means the model's over it. It's below it. So that means the model predicted this many more bursts than the truth. So 1.7, we're just subtracting. Well, that's called an extrapolation of the model. So we can actually do that. It's a horrible utilization of the model, but we can extrapolate and go outside the bounds. Ian, good to see you there. We're doing in person right now. I'm going to go outside here in a moment. That would be the interpolation right there. 2020 is just going to be the year 120. And we just take right here and grab this number. And there we go. It says 1 decimal. So I guess it's going to round, right? Yeah. And then this is a bit of an extrapolation. We're going outside the model. I would say there's only a tiny... Awesome, Ian. I'll be outside here in a second. We'll finish up this problem. And Dee Dee, so good to see you. I would say there's a tiny bit of faith because this model goes up to 2015. There's some faith because it's not a very large extrapolation going outside the X bounds of the model. And 2050 right there is going to be the year 150 because that's 150 years after. And once again, you can just plug in the numbers, but that's going to solve. I hope the regression solver should get it right. And I would say I have little faith. This is far beyond. It's a big extrapolation. I would say there's no faith because this is a big extrapolation. Let's see if we get it all correct. We did! And remember we said we're going to use that other number up here. It was like 17. So they must have a lot of leeway because they know solver programs can give different answers. See, there we go. So there is some leeway depending on how you choose to solve it. Because if it was 17, then the model is off by 2. So the model predicted 2 higher percent birth rate. Well, that's got it. We're going to hop outside. Thank you so much, everybody. Bye for now.